Now, in this lecture, we will answer on two questions. In the first question, we will find out the area of this semicircle that is inscribed by a quarter circle. And in the second question, we will find out the size of this angle theta, that is the angle of the right triangle ABC. Okay, so we'll start with the first question. In the drawing, we have a quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of this semicircle that is described by the quarter circle. So first of all, we will define the center of this semicircle as point O. In the next step, I will present to you a new rule. This is actually rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I will read rule number 2 again, rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have also tangent AB, here this tangent AB is tangent to this circle at this point. Point M is the point of tendency. Of tangent AB with this circle, and we also have the radius OM. O is the center of the circle, and OM is the radius of the circle. We have here the radius OM of the circle that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So I read rule number 1 again. According to rule number 1, a tangent to a circle, that is to say tangent AB to this circle, is perpendicular to the radius drawn to its point of tendency. Here the radius OM, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say this angle equals to 90 degrees, and this angle will be equal to 90 degrees according to rule number 1. We actually can implement rule number 1 in our drawing. Here we'll define this point as point A, this point is point B, we'll define this point as point C, this point is point D, we'll define this point as point E, we'll define this point as point F, and this point as point G. We'll join points O and B together by a straight line. Here, line segment OB is the radius of the semicircle. Why? Because line segment OC starts from the center of the semicircle, that is to say from point O, and ends at point B, that is a point on the semicircle itself. And this is exactly the definition of a radius. So OB is the radius of the semicircle, so we'll define the radius of the semicircle as R, therefore OB will be equal to R. So here we have the radius OB of the semicircle that is drawn to the point of tendency. That is to say, the radius OB is drawn to point B, that is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent AC will be perpendicular to the radius BO. So AC is perpendicular to BO, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we will join points O and D together by a straight line. Here, line segment OD is the radius of the semicircle because of the fact that it starts from the center of the semicircle and ends at point D, that is the point of the semicircle itself. Okay, so here we have the radius OD that is drawn to the point of tendency. That is to say, the radius OD, it is drawn to point D, that is the point of tendency of tangent CE with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then that tangent will be perpendicular to that radius. That is to say, CE will be perpendicular to DO, CE perpendicular to DO, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Again, whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent CE will be perpendicular to the radius OD. CE is perpendicular to OD, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. And we know that C is the center of the semicircle. And C is the center of the quarter circle, of course. C is the center of the quarter circle. I'll write it down. C is the center of the quarter circle. And angle ACE of the quarter circle must be equal to 90 degrees because of the fact that ACE in the quarter circle, angle ACE must be equal to 90 degrees. So actually, in quadrilateral BOCD, we have 1, 2, 3 right angles. Okay? I'll repeat again. In quadrilateral BOCD, we have 3 right angles. The sum of 3 right angles is 90 times 3, that is 270 degrees, plus the size of the fourth angle, that is actually angle BOD. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We will subtract 270 degrees from this equation, and we will get that the missing angle, angle BOD, it is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. It is equal to 90 degrees, so this angle equals to 90 degrees, angle BOD. So we actually found out that in quadrilateral BOCD we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we can relate to quadrilateral BOCD as a rectangle. Quadrilateral BOCD is a rectangle. And we have also rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. So according to rule number 2, the opposite sides of rectangle BOCD, they are equal to each other. That is to say, BO must be equal to CD according to rule number 2. BO equals to CD according to rule number 2. But BO equals to R. According to what we have already found out, BO equals to R. So from this equation, R equals to BO equals to CD, we will derive that CD is also equals to R. Okay, CD is also equals to R. Likewise, according to rule number 2, OD must be equal to BC. OD must be equal to BC according to rule number 2. That the opposite sides of a rectangle are equal to each other. But OD equals to R according to what we have already found out. OD equals to R. So from this equation, R equals to OD equals to BC, we will derive that BC is also equals to R. BC equals to R. Here we can write here that BC equals to R. So actually we found out that all the sides of quadrilateral BOCD are equal to each other, they are equal to R, and it has also 4 right angles, therefore quadrilateral BOCD is not a rectangle but a square. So we can write down that quadrilateral BOCD is a square. Okay, in the next step we will join points O and C together by a straight line. Actually, line segment CO is the diagonal of square BOCD. We'll find out the length of line segment CO by implementing the Pythagoras theorem on the green right triangle OCD. So in the green right triangle OCD, we will get that according to the Pythagoras theorem, PT is a variation from Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is CO square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to CD square plus OD square. I repeat again, according to the Pythagoras theorem and the right green triangle OCD, we get that CO square equals to CD square plus OD square according to the Pythagoras theorem. So CO square equals to CD square. CD equals to R, so CD square will be equal to R square plus OD square. OD equals to R, so OD square will be equal to R square. So in conclusion, we found out that CO square equals to R square plus R square. That is to say, CO square equals to R square plus R square, that is 2R square. Here we will take a root out of this equation, and we will get that CO equals to the square root of 2 times R. So the diagonal of square COBD equals to square root of 2 times R in its length. So we can write here that the diagonal CO of the square equals to square root of 2 times R. In the next step, we will extend the diagonal CO by a straight line until it touches the quarter circle at this point S. Point S is the touching point of the extended diagonal CO and the quarter circle. And we will find out the length of the short line segment OS. It is OS or SO, it is the same. The length of line segment OS, it is very easy to see from the drawing. that it is equal to CS minus CO. CS minus CO. I repeat again, the length of the short line segment OS equals to CS minus CO. So OS equals to CS. What is the length of line segment CS? C is the center of the quarter circle. S is the point of the quarter circle itself. This is exactly the definition of a radius. Therefore, and we know that the radius of the quarter circle is equal to 3 units. So CS equals to 3 units minus CO. We already found out that CO equals to square root of 2 times R. In conclusion, we found out that the short line segment OS equals to 3 minus square root of 2R. So we can write here that the length of the short line segment OS is equals to 3 minus square root of 2R. Okay. In the next step, we will complete the quarter circle to a circle. So we created a circle from the quarter circle. In the next step, we will extend diagonal OC by a straight line until it touches the circle. At point M. Point M is the touching point of the extended diagonal OC in the circle. So what is the length of line segment MC? The length of line segment MC, C is the center of the quarter circle, M is the point of the circle itself. This is exactly the definition of a radius. So the radius of the circle equals to the radius of the quarter circle, that is to say it is equal to 3 units. Okay? In the next step I will present to you a new rule that will be rule number 3. According to rule number 3, if chord AB intersect with chord CD, at point O. Point O is the intersection point of chord AB with chord CD. Then the following formula is true, that AO times OB equals to CO times OD. So here we have chord AB This is chord AB that intersects with chord CD. This is chord CD. And the intersection point between chord AB and chord CD is at point O. So, if this is the condition that we have chord AB that intersects with chord CD at point O, then the following formula is true, that AO over OB equals to CO over OD. Again, AO times OB equals to CO times OD. So we actually can implement rule number 3 in our drawing, because in our drawing we have chord SM that intersects with chord GF at point O. Point O is the intersection point of chord SM with chord GF. Here we repeat again. In our original drawing, chord SM intersects with chord GF at point O. Then according to rule number 3, we will get that MO times OS equals to GO times OF. I repeat again, according to rule number 3, we'll get that MO times OS equals to GO times OF. Here, MO equals to, from the drawing, it is very easy to see that MO, line segment MO equals to MC plus CO. And we've already found out that OS equals to 3 minus square root of 2R. And it is equal to GO. What is the size of line segment GO? O is the center of the semicircle. G is a point on the semicircle itself. This is exactly the definition of a radius. That is to say, OG or GO is the radius of the semicircle. That is to say, it is equal to R. For the same reason, OF will be also equal to R. Line segment OF starts from the center of the semicircle and ends at point F, that is a point on the semicircle itself. Therefore, OF is the radius of the semicircle, that is to say it is equal to R. So GO equals to R, and OF it is also equals to R. R times R is R squared. Here MC equals to 3. CO equals to square root of 2 times R. So 3 plus square root of 2 times R times 3 minus square root of 2 times R must be equal to R squared. This expression 3 plus square root of 2 times R times 3 minus square root of 2 times R, it is very similar to the algebraic identity that states that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to 3 and B equals to square root of 2 times R. So we know that A plus B times A minus B equals to A squared minus B squared. Therefore this expression 3 plus square root of 2R times 3 minus square root of 2R must be equal to A squared minus B squared according to this trigonometric identity. That is to say it must be equal to A squared, that is 3 squared, that is equal to 9, minus B squared. B is square root of 2 times R. B squared is square root of 2 squared, that is 2 times R squared. So in conclusion, B squared is 2R squared. So in conclusion, we found out that this expression equals to 9 minus 2R squared, and it is also equals to R squared. Or actually we found out that nine minus 2R squared equals to R squared. We will add R squared, we will add 2R squared to this equation, and we get that 9 equals to 2R squared plus R squared is 3R squared. We will divide this equation by 3 and we get that 3R squared over 3 is R squared. So R squared equals to 9 over 3, that is 3. So we found out that R squared equals to 3. What is the area of the semicircle? The area of the semicircle equals to the area of the circle over 2. That is to say it is equals to pi r squared, that is the area of the circle over 2. So it is pi r squared over 2. We have already found out that r squared is 3, so we substitute r squared by 3, so it will be pi and r squared is 3 over 2. So in conclusion, the area of the semicircle equals to 3 pi over 2 square units, so in terms of numbers it is equals to 4.71 square units. Okay, I'll repeat again, the area of this semicircle equals to either 3 pi over 2 square units, or in terms of numbers it is equal to 4.71 square units. We finished with the first method. In the next step I will present to you how to find out the area of the semicircle according to the second method. In the second method, we will use all the things that we have already found out in the first method. Now here, this is point O, that is the center of the semicircle. This is point A, point B, point C, point D, point E, point F, and point G. We have already found out that quadrilateral BOCD is a square, and diagonal CO of the square is equal to square root of 2 times R. We have already found out that GO is the radius of the semicircle, that is to say it is equal to R, and OF, it is also the radius of the semicircle, that is actually equals to R. In the next step, we will join point C and G together by a straight line. What is the length of line segment CG? C is the center of the quarter circle. G is the point of the quarter circle itself. And that is exactly the definition of a radius. That is to say, line segment CG is the radius of the quarter circle that is actually equal to 3 units. For the same reason, if you join point C and F together by a straight line, CF will be equal to the radius of the quarter circle, that is to say, it will be equal to 3 units. I repeat again that C is the center of the quarter circle and F is the point of the quarter circle itself. Therefore, CF is the radius of the quarter circle, that is to say, it is equal to 3. So, I will copy triangle GCF in a new page, and we will analyze this triangle GCF or CGF. So this is triangle CFG, and because of the fact that side CF equals to side CG in triangle CFG is an isosceles triangle. And FG is the base of the isosceles triangle CFG. Okay, FG is the base, and CO is the median to the base. CO is the median to the base why CO is the median to the base? Because of the fact that line segment CO divides the base FG into two equal parts. FO equals to OG equals to R. And we have also rule number 4 that is related to the median to the base of an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So I'll read rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So here we have the median CO to the base FG of the isosceles triangle CFG. And according to rule number 4, the median CO to the base FG is perpendicular to the base. That is to say, CO is perpendicular to FG. CO is perpendicular to FG. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. Okay, here also we know that the median CO is perpendicular to the base GF, that is to say, according to rule number 4, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So in the next step we will implement the Pythagoras theorem on the right triangle, triangle COG. Okay, this triangle, triangle COG. So I will copy the right triangle, triangle COG in a new page, and we will implement the Pythagoras theorem on this green right triangle, triangle COG. So this is the right green triangle, triangle COG. And And according to the Pythagoras theorem, here PT is the relation for Pythagoras theorem, we get that the square of the hypotenuse equals to the sum of the square of the perpendiculars. That is to say, CG squared equals to CO squared plus OG squared. CG equals to 3, so CG squared is 3 squared, that is 9. It is equals to CO squared. CO equals to square root of 2r. Therefore, CO squared will be equal to 2r squared plus OC squared plus OG squared. OG equals to r. Therefore, OG squared will be equal to r squared. So we got that 9 equals to 2r squared plus r squared, that is 3r. 3r squared. We divide this equation by 3 and we get that 3r squared over 3 is r squared equals to 9 over 3, that is 3. So we found out that r squared equals to 3. And the area of the semicircle equals to pi r squared over 2. We substitute r squared by 3. And we get that the area of the semicircle equals to pi times 3 over 2. That is to say, it is equals to either 2 pi over 3 square units, or in terms of numbers, it is equals to 3.71 square units, exactly what we have already found out, exactly as we have already found out in the first method. So we finish with the first question. In the next step I will present to you the second question, and we will solve the second question in two different methods. In the drawing, we have the right triangle, triangle ABC, angle ABC equals to 90 degrees, side BC of triangle ABC equals to 6 units, line segment DE equals to 2 units, and we also know that AE equals to EC, and we also know that line segment DE is perpendicular to AC, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. And we want to find out the size of this angle, angle theta, that is actually also going to be AC. So in order to find out the size of this angle, angle theta, we will make a construction. From point E, we will draw perpendicular on BC. So this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point E and BC as F. We know that in the right triangle, triangle ABC, this angle equals to theta. This angle equals to theta, this angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta. In order to complete the sum of the angles, 280 degrees, this angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. So, from one side we know that this angle equals to 90 degrees minus theta. But from the other side, we will define this angle as angle alpha. Therefore, we can conclude from it that because of the fact from one side this angle equals to 90 degrees minus theta, and according to our definition it is also equals to alpha, we will conclude that alpha equals to 90 degrees minus theta. Okay? alpha equals to 90 degrees minus theta. Here we will add to this equation theta, and we will also subtract alpha, and we will get that angle theta equals to 90 degrees minus alpha. Yeah. Okay, so in the right triangle EFC, we know that this angle equals to alpha, so this angle must be equal to 90 degrees minus alpha. In order to complete the sum of the angles 280 degrees, this angle must be equal to 90 degrees minus alpha. So here we have angle, what is the size of this angle? Angle DEF. Angle DEF, this angle, from the drawing it is very easy to see that angle DEF will be equal to angle DEC, the big angle, minus angle FEC. Angle DEC minus angle FEC will give us the missing angle, angle DF. So write it down. The size of angle DEF will be equal to angle DEC minus angle FEC. I'll repeat again. Angle DEC minus angle FEC equals to angle DEF, the missing angle. So angle DEF is equal to angle DEC according to what is given as the question. This is the right angle, so we'll substitute angle DEC by 90 degrees. And we have already found out that this angle equals to 90 degrees minus alpha, so we substitute this angle EC by 90 degrees minus alpha. And we get that the missing angle, angle DEF, equals to 90 degrees. We'll open the brackets here, so we'll get that 90 degrees minus 90 degrees is 0. And there minus and minus is plus, so it is plus alpha. So in conclusion, we found out that the missing angle, angle DEF, equals to alpha. So this angle equals to alpha. So if this angle equals to alpha, this angle equals to 90 degrees, so in the right triangle DEF, this angle must be equal to 90 degrees minus alpha. Okay? But because of the fact that 90 degrees minus alpha equals to theta, we can substitute 90 degrees minus alpha by theta. We'll do it now. We'll substitute this angle, this is 90 degrees minus alpha by theta. And this angle equals to theta. And we will define side DF as x. We'll define side EF as y. We'll define line segment AE as A. And if AE equals to A, and we know that AE equals to EC, then EC must be also equal to A because they are equal to each other. In the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EFC, this right triangle. So why triangle ABC is similar to triangle EFC? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle ABC of triangle ABC is equal to this angle, angle EFC, of triangle EFC, and they are both equal to 90 degrees. I'll repeat again. Angle ABC equals to angle EFC, and they are both equal to 90 degrees. In addition, we know that 90 degrees minus alpha equals to theta. So here we can write down that 90 degrees minus alpha equals to theta according to this equation. In addition, those two angles, they are both equal to theta, therefore they are equal to each other. So we can write down that angle BAC equals to angle FEC, and both angles are equal to theta. I'll repeat again, angle BAC equals to angle FEC, and they are both equal to theta. Finally, this angle is a common angle, it belongs to both triangles. So we can write down that angle ACB, triangle ABC, is equal to angle ECF of triangle EFC, and it is equal to alpha. It is a common angle. Actually, we are saying that this angle equals to itself because it belongs to both triangles. It is a common angle, it belongs to both triangles. I'll repeat again. Angle ACB equals to angle ECF equals to alpha. It is a common angle that belongs to both triangles. So we proved that all the angles of triangle ABC, the big right triangle, can go into all the angles of triangle EFC, this triangle. Why? Because those two angles, they are both equal to theta, they are both equal to each other. Therefore, they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And this is a common angle that belongs to both triangles. Therefore, we proved that triangle ABC is similar to triangle EFC according to angle similarity rule. So I write it down. We actually proved that the right big triangle, triangle ABC, is similar. This is the sign of similar to the right triangle, triangle EFC according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over AC in triangle ABC is equal to EF over EC in triangle EFC. Okay, from the fact that the two right triangles are similar to each other, we conclude that AB over AC equals to EF over AC. So AB over AC. AC, the hypotenuse AC equals to A plus A, that is to say it is equals to 2A, so we substitute AC by 2A. And it is equal to EF. EF equals to Y according to our definition over EC. EC equals to A also according to our definition. So in conclusion, we found out that AB over 2A equals to Y over A. Here we have A on both sides of the equation, so A will get cancelled, and we're left only with AB over 2 that is equal to Y. Here we will multiply this equation number 1 by 2, and we get that according to equation number 1, AB equals to 2Y. AB equals to 2Y. So we can write here that AB equals to 2Y. In the next step, we'll prove that the right big triangle, triangle ABC, is similar to the right small triangle, this triangle, triangle ADF. So why those two triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle ABC and triangle ABC is equal to this angle, this is actually angle EFD. And both angles are equal to 90 degrees. I'll repeat again. Angle ABC equals to angle EFD, they are both equal to 90 degrees. In addition, we have those two angles, they are both equal to alpha, therefore they are equal to each other. So angle ACB is equal to angle DEF, this angle, and they are both equal to alpha. I'll repeat again. Angle ACB equals to angle DEF, and they are both equal to alpha. Finally, those two angles, they are both equal to theta, therefore they are equal to each other. Okay. So here we have angle BAC, this angle, and triangle ABC is equal to this angle, this is actually angle EDF. And both angles are equal to theta. And repeat again that angle BAC equals to angle EDF, and they are both equal to theta. So we prove that all the angles of triangle ABC can go into all the angles of triangle EDF. Why? Because those two angles are equal to each other, they are both equal to theta. Those two angles are also equal to each other because they are both equal to alpha. And those two angles are equal to each other because of the fact that they are both equal to 90 degrees. So triangle ABC is similar to triangle EDF according to angle similarity rule. I repeat again, triangle ABC is similar to triangle EDF according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over BC is equal to AB over BC equals to DF over EF. I'll repeat again, from the fact that triangle ABC is similar to triangle EDF, we will conclude that AB over BC equals to DF over EF. So here, AB equals to 2y, so we'll substitute AB by 2y over BC. BC equals to 6, so we'll substitute BC by 6. And it is equals to DF, DF equals to x, we'll substitute DF by x over EF. EF equals to y, so we'll substitute EF by y. Okay. So here, in this set of equation number 2, we divide this set of equation number 2 by 2, and we will get that 2y over 2 is y, and 6 over 2 is 3, is equal to x over y. Here, we will cross multiply this equation number 2, and we will get that y squared is equal to 3x. Okay. We will focus on the right triangle, triangle EDF. In the right triangle, triangle EDF, according to the Pythagoras theorem, we will get that x squared plus y squared equals to 2 squared. X squared plus y squared equals to 2 squared, that is 4. According to equation number 3, we know that x squared plus y squared equals to 4, so we can substitute here y squared in this equation number 3 by 3x, because y squared equals to 3x according to equation number 2. We'll do it now and we'll get, according to equation number 3, x squared plus y squared, that is 3x, equals to 4. So here we'll subtract 4 from this equation number 3, and we'll get that according to equation number 3, x squared plus 3x minus 4 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X is equals to minus b plus minus square root of b squared minus 4 times ac over 2a in our specific quadratic equation. The coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we'll put the data inside the formula for x and we'll find out the value of the values of x. So we'll get that x equals to minus b. B is 3, so minus 3 is minus 3. B is equals to 3, so minus b is equal to minus 3 plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 1, times c is minus 4. Over 2a. A is 1, so 2a is 2 times 1, that is 2. So we got here that x equals to minus 3 plus minus. Here we have minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So inside the root we have left only with 25 over 2. So here we have x equals to minus 3 plus minus square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution for x is x equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. But because of the fact that ax is the length of side df, of triangle EDF, x is the length, so it must be a positive number. X is the length, and therefore it must be a positive number. It can never be equal to minus 4, this is a negative number, so we'll cancel the solution, and we're left only with the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we actually found out that x2 equals to 1. So I will copy the right triangle DEF, and we will find out the cosine theta of the right triangle DEF. Okay? So triangle EDF is the right triangle, so in the right triangle EDF we will get that cosine theta equals to df over dE. df is 1, dE is 2. So in conclusion we found out that cosine theta equals to 1 half. So if cosine theta equals to 1 half, we get that theta itself equals to 60 degrees. So we found out that the missing angle theta, the angle that we are looking for, it is equal to 60 degrees. In the next step I will present to you a second method to find out the size of angle theta. Okay? We will define angle ACB as alpha. In the first method we found out that this angle also equals to 90 degrees minus theta. So actually we have the equation here. We have here the equation that alpha equals to 90 degrees minus theta. In the next step I will copy the right triangle ABC in a new page, and we will analyze the right triangle ABC. we will define AE as A, and because of the fact that A equals to EC, EC will be also equal to A, so the hypotenuse AC equals to A plus A, that is 2A. So this is the right triangle ABC that I copied to this new page. Here we know that cosine alpha in the right triangle ABC, cosine alpha equals to BC over AC. BC equals to 2A and AC equals to 6. We will divide both the numerator and the denominator of this side of equation number 1 by 2, and we get that 2A over 2 is A, and 6 over 2 is 3. So in conclusion, we found out that according to equation number 1, cosine alpha equals to A over 3. We will multiply this equation by 3, and then we will divide it by, here, actually, here, cosine alpha equals to BC over AC, yes? BC equals to 6. Here, BC equals to 6. And AC equals to 2A. Okay? So we divide the numerator and the denominator of this side of equation number 1 by 2, and we get that 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha according to equation number 1 equals to 3 over A. Here we multiply this equation number 1 by A, and then we divide it by 3. And then we will divide it by cosine alpha, and we will get that A equals to 3 over cosine alpha. We multiply it by A, and then we divide it by cosine alpha, and we got that A equals to 3 over cosine alpha according to equation number 1. Found out that A equals to 3 over cosine alpha. In the next step, I will copy the right triangle EDC, and we will analyze the right triangle EDC. So this is the right triangle EDC that I copied from the original drawing. In the right triangle EDC, we know that tangent alpha equals to DE over EC. D equals to 2 and EC equals to A. So in conclusion, we found out that according to equation number 2, tangent alpha equals to 2 over A but according to equation number 1, we have already found out that A equals to 3 over cosine alpha. We will substitute A in equation number 2 by 3 over cosine alpha, because 3 over cosine alpha equals to A according to equation number 1. So we'll do it now, and we will get that according to equation number 2, tangent alpha equals to 2 over A, but A according to equation number 1 equals to 3 over cosine alpha. So we will move cosine alpha to the numerator and 3 to the denominator, and we get it according to equation number 2, tangent alpha equals to 2 times cosine alpha over 3. We substitute tangent alpha by sinus alpha over cosine alpha, and we get that sinus alpha over cosine alpha equals to 2 times cosine alpha over 3. Here we'll cross multiply this equation, equation number 2, and we get that according to equation number 2, 3 times sine alpha equals to 2 times cosine square alpha. We have the trigonometric identity that states that sine square alpha plus cosine square alpha equals to 1. We subtract sine square alpha from this trigonometric identity, and we get that cosine square alpha equals to 1 minus sine square alpha. So we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We'll do it now, and we get that according to equation number 2, sine alpha equals to 2 cosine square alpha. But cosine square alpha, according to this trigonometric identity, equals to 1 minus sine square alpha. We'll open the brackets on this side of equation number 2, and we get that 3 sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sinus square alpha. We will add 2 sine square alpha to this equation, equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. We subtract 2 from this equation, equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. We have here a quadratic equation. The missing variable in this quadratic equation is sinus alpha, so x equals to sinus alpha. And the formula to solve out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Now a specific quadratic equation. The coefficient A equals to 2. The coefficient B equals to 3. And the coefficient C equals to minus 2. And the missing variable is sinus alpha. So x equals to sinus alpha, so we'll put the data inside this formula and we get that sinus alpha equals to minus b. B equals to 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 2, so there's minus 4 times 2, times c is minus 2, over 2a. A equals to 2, so 2 times 2 is 4. So in conclusion, from now that sinus alpha equals to minus 3 plus minus square root of minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, and 16 plus 9 is 25. So inside the root we're left only with 25 over 4. So we found out that sinus alpha equals to minus 3 plus minus, the square root of 25 is 5 over 4. So here we will have two solutions that are possible for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8. And minus 8 over 4 is minus 2. So actually we found out that sinus alpha, according to the first solution, it is equals to minus 2. But because of the fact that the function sinus alpha can accept values that are ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can accept, this solution is the incorrect solution. In other words, sinus alpha cannot never be equal to minus 2. So we cancel this solution and we're left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 half. So if sinus alpha equals to 1 half, it means that alpha itself equals to 30 degrees. And we have this equation that alpha equals to 90 degrees minus theta. We just now found out that alpha equals to 30 degrees, so we'll substitute alpha by 30 degrees, and we get that 30 degrees equals to 90 degrees minus theta. We will add theta to this equation and we'll subtract alpha, and we will get that angle theta equals to 90 degrees minus 30 degrees, that is actually equals to 60 degrees. So we found out that the size of angle theta, the angle that we are looking for, is equal to 60 degrees. So this angle theta equals to 60 degrees. So in the next step I will summarize the lecture. We'll start with the first question. In the first question, we have a semicircle that is inscribed by quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. So we defined this point, the center of the semicircle, is point O, and then I presented to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have tangent AB to this circle, tangent AB is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. That is to say, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So we can implement rule number 1 in our drawing. Here we connected points O and B together by a straight line. OB is the radius of the semicircle, because it starts from the center of the semicircle, that is to say from point O, and then at point B, that is a point on the semicircle itself. And this is exactly the definition of a radius. So we have the radius OB that is drawn to the point of tendency, that is to say the radius is drawn to point B, that is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent AC will be perpendicular to the radius BO. So AC is perpendicular to BO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we connected points A, O, and D together by a straight line. OD is the radius of the semicircle, and we have the radius OD that is drawn to the point of tendency, that is to say it is drawn to point D, that is the point of tendency of tangent CE with this semicircle. And whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, tangent CE will be perpendicular to the radius DO. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. And because of the fact that ACE is a quarter circle, point C must be the center of the quarter circle, and angle ACE must be equal to 90 degrees. So in quadrilateral BOCD, we have 1, 2, 3 right angles. In quadrilateral BOCD, we have 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of the fourth angle, that is angle BOD. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation, and we found out that the missing angle, angle BOD, equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. Here, this angle equals to 90 degrees. Therefore, in quadrilateral BOCD, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we can relate to quadrilateral BOCD as a rectangle. And we have also rule number 2, that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle BOCD, they are equal to each other. It means that BO equals to CD. BO equals to CD, but BO equals to R. We already found out that BO equals to R. Here BO equals to R, and from this equation R equals to BO equals to CO, we will get that R equals to BO equals to CD. We will get that CD is also equals to R. Here CD is also equals to R. Likewise, according to rule number 2, OD must be equal to BC. OD must be equal to BC, but we have already found out that OD equals to R. Here OD equals to R, so from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. Here BC is also equals to R, therefore quadrilateral BOCD has 4 equal sides and 4 right angles. Therefore quadrilateral BOCD is not a rectangle but a square. So quadrilateral BOCD is a square. Then we join points O and C together by a straight line. The OC, 9-segment OC, is the diagonal of square BOCD. In order to find out the length of diagonal OC, we implemented the Pythagoras theorem on the right triangle COD. According to the Pythagoras theorem, PT is a relation from Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CO square equals to CD square plus OD square. So CO square equals to CD square, CD equals to R, so CD square is R square plus OD square. OD equals to R, so OD square is R square. So in conclusion, we found out that CO square equals to R square plus R square plus R square is 2R square. CO square equals to 2R square, we took out of this equation and found out that CD equals to square root of 2 times R. Okay, so we can write here that the length of diagonal CO equals to square root of 2 times R. R is the radius of the semicircle. Then we extended diagonal CO by a straight line until it touches the quarter circle at point S. So we created it here, the small line segment OS. The length of line segment OS is very simple to see from the drawing that the length of the small line segment OS equals to SC minus OC. Again, the length of the short line segment OS equals to SC or CS minus CO. So OS equals to CS. C is the center of the quarter circle. S is the point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, CS equals to the radius of the quarter circle that is equal to 3 units. So CS equals to 3, and we only found out that CO, the diagonal of the square, equals to square root of 2 times R. So in conclusion, we found out that OS equals to 3 minus square root of 2R. The length of line segment OS equals to 3 minus square root of 2R. Then we completed the quarter circle to a circle. We extended diagonal OC by a straight line until it touches the circle at this point, point M. Point M is the touching point of the extended diagonal OC in the circle. What is the length of line segment CM? C is the center of the quarter circle and also the center of the circle itself. M is the point of the circle itself. Therefore, CM is the radius of the circle. That is to say, it is equal to 3 because the radius of the circle is equal to the radius of the quarter circle, that is equal to 3. Okay, then I presented to you rule number 3. According to rule number 3, if chord AB is chord AB intersects with chord CD, this is chord CD, at point O. Here point O is the intersection point of chord AB with chord CD. Then the following formula is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule number 4 in our drawing. Because in our drawing we have the chord SM that intersects with chord GF, chord SM that intersects with chord GF at point O. Point O is the intersection point. I'll repeat again, chord SM intersects with chord GF at point O. Point O is the intersection point of chord SM with chord GF. Therefore, according to rule number 4, we'll get that MO times OS equals to AO times OF. Again, MO times OS equals to AO times OF. Again, MO times OS equals to GO times OF. What is the value of MO? From the drawing, it's very easy to see that MO equals to MC plus CS. Okay, MO equals to MC plus CS. MO equals to, again, MO equals to MC plus CO. Okay, MO equals to MC plus CO. OS, we already found out that OS equals to 3 minus square root of 2R. GO is the radius of the semicircle, that is to say it is equal to R, and OF, it is also the radius of the semicircle, that is to say it is equal to R. So GO times OF is R times R, that is R squared. Here MC equals to 3 units, it is the radius of the quarter circle, and CO equals to square root of 2 times R. So in conclusion, MC plus CO is 3 plus square root of 2R times 3 minus square root of 2R must be equal to R squared, according to rule number 3. This expression is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. Here A equals to 3 and B equals to square root of 2 times R. A squared is 3 squared, it is 9, B squared is 2R squared. So in conclusion, this expression equals to 9 minus 2R squared, and it is equal to R squared. We added 2R squared to this equation and we found out that 2R squared plus R squared is 3R squared, 3R squared equals to 9. We divided this equation by 3 and we found out that R squared equals to 3. And the area of the semicircle equals to pi R squared over 2. We have already found out that R squared equals to 3, so we substitute R squared by 3 in this equation, and found out that the area of the semicircle equals to either 3 pi over 2 square units, so in terms of numbers it is equal to 4.71 square units. We finished with the first method. The next step, I present to you how we found out the area of the semicircle according to the second method. In the second method, we used the thing that we already found out in the first method. We have already found out in the first method that BOCD is a square, and the diagonal of this square CO equals to square root of 2 times R. GO, it is the radius of the semicircle that is equal to R. OF, it is also the radius of the semicircle that is equal to R. Then we connected points C and G together by a straight line. CG is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle and ends at point G, that is the point on the quarter circle itself. Therefore, CG is the radius of the quarter circle, that is to say it is equal to 3 units. Likewise, from the same reason, CF, it is the radius of the quarter circle, that is also equal to 3 units, of course. So we created here triangle CGF. I copied the triangle CGF in this new page. We already found out that CF equals to CG, that is 3 units. And because of the fact that CF equals to CG, triangle CGF is an isosceles triangle. The base of the isosceles triangle is FG, and CO is the median to the base. Why? Because the median to the base CO, or line segment CO, bisects the base FG into 2 equal parts. That is to say, FO equals to OG equals to R. For that reason, CO is the median to the base. And we have also 1 over 4 that states that the median to the base in an isosceles triangle is perpendicular to the base. So here we have the median CO. The median CO to the base FG is perpendicular to the base. So according to rule number 4, CO is perpendicular to FG. Again, CO is perpendicular to FG. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. Okay? We have already found out that CO, that is the diagonal of the square, is square root of 2 times R. OG equals to R and FO equals to R. So here I copied the right triangle COG in a new page, and we implemented the Pythagoras theorem on the right triangle COG. This is the right triangle COG. Here, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say CG square equals to CO square plus OG square. CG equals to 3, so CG square is 3 squared, it is 9. It is equal to CO squared. CO is also, CO is square root of 2 times R, so CO squared is square root of 2R squared, it is 2R squared. OG is R, so OG squared is R squared. So in conclusion, we found out that 9 equals to 2R squared plus R squared. 2R squared plus R squared is 3R squared, so we found out that 9 equals to 3R squared. We divided this equation by 3 and we found out that R squared equals to 3. We know that the area of the semicircle equals to pi R squared over 2. We substituted R squared by 3. And we got that the area of the semicircle equals to either 2 pi over 3 square units, or in terms of numbers, it is equal to 4.71 square units. Okay, so we finished with question number 1. In the next step, I will present to you how we solved the second question. In this question, we have right triangle. Triangle ABC is a right triangle. We know that side BC equals to 6 units, angle ABC equals to 90 degrees, side D and line segment DE equals to 2 units, and D is perpendicular to the hypotenuse AC, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees, and we also know that AE equals to EC. And we want to find out the value, the size of angle BAC, that is actually equals to theta. In order to find out the size of angle theta, we made a construction. From point E, we move perpendicular on BC. That is to say, this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to our construction. And we defined the touching point of the perpendicular from point E and BC as F. Then we defined this angle as angle alpha. And because of the fact that in that triangle ABC, this angle equals to 90 degrees and this angle equals to theta, this angle must be equal to 90 degrees minus theta. So from one side this angle equals to alpha, and from the other side this angle also equals to 90 degrees minus theta. From those two things we will derive that alpha equals to 90 degrees minus theta. So alpha equals to 90 degrees minus theta. We added to this equation theta and we subtracted alpha, and we found out that theta equals to 90 degrees minus alpha. Then we found out the size of this angle, angle DEF, this angle. This angle, but before that, in the right triangle FEC, if this angle equals to alpha, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle FEC, 280 degrees. So this angle must be equal to 90 degrees minus alpha. So what is the size of the angle DEF? Angle DEF will be equal to angle DEC minus angle FEC. Angle DEF equals to angle DEC minus angle FEC. So angle DEF equals to angle DEC, that is 90 degrees according to what is given as the question. And we already found out that angle FEC equals to 90 degrees minus alpha. So we substituted angle FEC by 90 degrees minus alpha. We opened the brackets here and we found out that angle DEF equals to 90 degrees minus 90 degrees, that is 0. Minus and minus is plus. So in conclusion, we found out that this angle DEF equals to alpha. Then we proved that the right big triangle ABC is similar to the right small triangle FEC. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other because both of them are equal to 90 degrees. Therefore, they are equal to each other. Okay? In addition, those two angles are both equal to theta, therefore they are equal to each other. And finally, this angle equals to itself is a common angle that belongs to both triangles. So we actually proved the triangle ABC similar to triangle EFC according to angle similarity rule, and from the fact that those two triangles are similar to each other, we will derive that AB over AC in the right triangle ABC equals to EF over EC in the right triangle EFC. Again, AB over AC equals to EF over EC. So AB is AB over AC. AC is A plus A, this is 2A, so we can substitute AC by 2A. EF equals to Y according to our definition. And EC equals to A. EC equals to A. So in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. We divided this equation, we have A on both sides of equation number 1, so A will get cancelled and we left only with AB over 2 that is equal to Y. We multiply this equation by 2 and we got that AB equals to 2Y. So we can write here that AB equals to 2Y. Then we proved that the right big triangle ABC is similar to this right small triangle, triangle DEF. Why those two triangles are similar to each other? First of all, those two angles, they are both equal to theta, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles, they are both equal to alpha, therefore they are equal to each other. So actually we proved that the right big triangle ABC is similar to the right small triangle in DF according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will derive that AB over BC equals to DF over EF. Again, AB over BC equals to DF over EF. AB equals to 2Y, so we substituted AB by 2Y. BC equals to 6, so we substituted BC by 6. DF equals to X. EF equals to Y. So in conclusion, we found out that 2Y over 6 equals to X over Y. We divided both the numerator and the denominator on this side of equation number 2 by 2, and we got that 2Y over 2 is 2, and 6 over 2 is 3. So in conclusion, we found out that according to equation number 2, Y over 3 equals to X over Y. We could multiply this equation number 2, and we got that Y squared equals to 3X. But if you focus on the right triangle here, according to the Pythagoras theorem, it is very easy to see that xy, according to the Pythagoras theorem, x squared plus y squared must be equal to 2 squared. That is to say, according to equation number 3, x squared plus y squared must be equal to 2 squared, that is 4. But according to equation number 2, y squared equals to 3x, so we can substitute y squared in this equation number 3 by 3x. We did it, and we got that x squared plus 3x equals to 4. We substituted 4 from this equation number 3, and we got the quadratic equation that x squared plus 3x minus 4 equals to 0. The general formula for quadratic equation is ax squared plus bx plus c equals to 0. A, B, and C are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, a equals to 1, b equals to 3, and c equals to minus 4. So we put the data inside the formula for x, and we found out the value of the values of x. Here x equals to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared. b equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, and c is minus 4 over 2a. a is 1, so 2 times 1 is 2, so here we found out that x equals to minus 3 plus minus 4 times minus 4 is 16, and 16 plus 9 is 25. So inside the root we left only with 25. All divided by 2, so here x equals to minus 3 plus minus the square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution for x is x equals to minus 3 minus 5 over 2, minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 3. So we found out that x1 equals to minus 4. But because of the fact that x is a length, it can never be a negative number, so we will cancel this solution, We cancel the solution and we left only with the second solution that x equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2 and 2 over 2 is 1. So we found out that x equals to 1, so I copied the right triangle EDF in a new page and we found out that the cosine theta of this angle in the right triangle EDF. This is the right triangle EDF, that's the copy from the original drawing. This is angle theta. We know that EF equals to y, DF equals to 1, and the hypotenuse DE equals to 2 according to what is given as the question. Here in the right triangle EDF, we know that cosine theta equals to DF over DE. DF is 1 because x equals to 1 and D is 2. So in conclusion, we found out that cosine theta equals to 1/2. So if cosine theta equals to 1/2, it means that theta itself equals to 60 degrees. So we found out that the side of this angle theta, the angle that we are looking for, it is equal to 60 degrees. We finished with the first method, and then I presented to you how to find out the size of angle theta according to the second method. We found out the size of angle theta according to the second method. Here we define this angle as alpha, so this angle must be equal also to 90 degrees minus theta, according to what we have already found out in this first method. We defined AE as A equals to EC, so if A equals to A, then EC must be also equal to A. So I copied the right triangle ABC in the new page and we analyze the right triangle ABC. This is the right triangle ABC. We know that A plus A is 2A, so for the hypotenuse AC is equal to 2A. BC equals to 6 is given as the question. So here cosine alpha in the right triangle ABC equals to BC over AC. BC equals to 6. AC equals to 2A. In conclusion, we found out that cosine alpha equals to 6 over 2A. We divided both the numerator of this side of equation number 1 by 2, and we got that 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha according to equation number 1 equals to 3 over A. Here we multiplied the equation number 1 by A, and then we divided it by cosine alpha, and we found out that A equals to 3 over cosine alpha according to equation number 1. Then we focused on the right triangle ABC. We focused on the right triangle DEF, so I copied the right triangle DEF in a new page, and we analyzed the right triangle DEC. We copied the right triangle DEC. Okay, and we analyzed the right triangle DEC. In the right triangle DEC, EC equals to A, this angle equals to alpha according to our definition, and D equals to 2 according to what is given as the question. So in this right triangle, we know that tangent alpha, the triangle EDC, tangent alpha equals to DE over EC. DE equals to 2. EC equals to A. So in conclusion, we found out that tangent alpha equals to 2 over A, according to equation number 2. Now we can substitute A in this equation number 2, by 3 over cosine alpha from equation number 1, because A equals to 5 over cosine alpha. Okay, so we did it and we got that tangent alpha equals to 2, and A is 3 over cosine alpha according to equation number 1. So we moved cosine alpha to the numerator and 300 to the denominator, and we found out that tangent alpha equals to 2 cosine alpha over 3. Because then we substituted tangent alpha by sinus alpha over cosine alpha, and we got that sinus alpha over cosine alpha equals to 2 times cosine alpha over 3. We multiplied this equation number 2, and we found out that 3 times sine alpha equals to 2 times cosine square alpha. Okay? Then we have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We substituted sine square alpha from this trigonometric identity, and we found out that cosine square alpha equals to 1 minus 1 minus sine square alpha. So we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha according to this trigonometric identity. We did it and we got that according to equation number 2, 3 sine alpha equals to 2 times cosine square alpha, but cosine square alpha equals to 1 minus sine square alpha according to this trigonometric identity. Okay? So we substituted cosine square alpha by 1 minus sine square alpha, and we got that 3 sine alpha equals to 2 times 1 minus sine square alpha. We open the brackets on this side of equation number 2, and we got that 3 times sinus alpha equals to 2 times 1, that is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. Okay? Then we added 2 times square alpha to this 2 times sine square alpha to this equation number 2, and we got that 2 times sine square alpha plus 3 times sine alpha equals to 2. We subtract the 2 from this equation number 2, and we got the 2 times sine square alpha plus 3 times sine square alpha minus 2 equals to 0. So we have here a quadratic equation. The missing variable in this quadratic equation is sinus alpha, and the general formula to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 2, the coefficient b equals to 3, and the coefficient c equals to minus 2. So here we put the data inside the formula for x, and we found out the value of the values of x, the values of sinus alpha, because x equals to sinus alpha. So here sinus alpha equals to minus b equals to 3, so minus b is minus 3, plus minus square root of b squared, b is 3, so b squared is 3 squared, that is 9, minus 4 times ac, a is 1, so minus 4 times a equals to 2, so it is minus 4 times a, that is 2, minus c, that is minus 2, over 2a, a is 2, so 2a is 2 times 2, that is 4. So we got that sinus alpha equals to minus 3 plus minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16. 16 plus 9 is 25. So inside the root we have left only with 25, and we have the equation that sinus alpha equals to minus 3 plus minus square root of 25 over 4. Square root of 25 is 5, so in conclusion we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we have two solutions are possible for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2. But because of the fact that the function sinus can accept values that are ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus can accept, this answer is a correct answer. The solution is a correct solution. In other words, sinus alpha can never be equal to minus 2. Therefore, we cancelled this solution, and we left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 half. So if sinus alpha equals to 1 half, it means that alpha itself must be equal to 30 degrees. And we have this equation that we have already found out even in the first method, that alpha equals to 90 degrees minus theta. Alpha equals to 90 degrees minus theta, and we just right now found out that alpha equals to 30 degrees, so we can substitute alpha by 30 degrees. We did it, and we got that 30 degrees according to this equation equals to 90 degrees minus theta. We added theta to this equation, and we subtracted 30 degrees, and we found out that the angle theta equals to 90 degrees minus 30 degrees, that is to say angle theta equals to 60 degrees. So we found out that the missing angle, that the angle that we are looking for, angle theta, equals to 60 degrees, according to the second method also. Okay, thank you very much.